Okay, so we're going to look at vectors, and some of this should be review, um, physics, or even from honors pre-calc, or even this class of dealing with parametrics. So there's going to be some overlap you're going to notice. This first video is going to focus on just getting a reminder of what vectors look like, and then the way they might show up on the AP exam, and then just differentiation of vector valued functions. The second video will focus on more of integrating vector valued functions. Okay, so really, if you look at our definition here in our notes, just as a vector, vector S, and it's a position vector. And if you remember, also maybe from physics or honors pre-calc, our position vectors are going to be represented by S. Where a velocity could be represented by V, and an acceleration could be represented by A. And you put those little vector hats above that letter or the arrow to indicate that it's a vector valued function. We could also look at the components, and the components would be set off by these not parentheses, but they're like almost like the ends of arrows. And there's two components. There's an X component and a Y component. And so it's pointing at that particular point at any moment of time t. Okay, so our first example says let f be a vector valued function, and here are the two components. And it represents the position of the particle at any time t. It says draw the path of the particle from t equals 0 to t equals 4. So I think it might also be useful to just kind of keep track of, what's happening at, not just 0 and 4, but all of those values. So like maybe up here I might say, okay, well, what is the vector at 0? And so I could say, okay, put in 0, 0, and then 0 minus 1 is negative 1 squared is 1. So I'd have 0, 1 as a vector, which means it's pointing from, these are all position vectors, so pointing from the origin, it's pointing to 0, 1. So it's pointing where is it at that moment in time. So the idea, again, like here's 0, 1, which is right here. So that's where it's at, and the vector that would be pointing there, could be represented. Pick this color. What a great color, brown. Could be represented like there. So that's the vector, and it's pointing to where it's at position 0. Okay. So then let's do f of 1. So, okay, the vector evaluated at 1 would be, again, 1 and then comma 0. And notice I'm putting it off as a vector because I want to indicate that I'm pointing to this point. I'm pointing to over 1, 0. So I'm pointing to that spot right there. So that's its position. And again, the vector that represents that is from the origin to that spot right there. So there's that vector. And then let's look at the position vector when t is equal to 2, and we'll do a couple here in a row. So then that would be 2, 2 minus 1 is 1, 1 squared is 1. I could do the vector at 3, and I should probably be good in terms of my notation. Put a little vector hat, use the vector symbol, 3, 3 minus 1 is 2, 2 squared is 4, and then the vector at 4, and I'll connect these here, 4, 9. So I'm going to go ahead and put in 2, 1, 2, 1, and then 3, 4, and 4, 9. And again, each of these represents one moment in time. And so the vector pointing there at time equals 2, the vector pointing there at time equals 3, and then the vector pointing here at time equals 4. But then it does say draw the path of the particle. So then I would want to actually draw in, kind of connect this. And your instinct should be good that it is forming a parabolic shape. And in fact, if you remember how to eliminate the parameter, you could simply just remember that this part is x and this part is y. And if you just do an algebra, if x is equal to t, and y is equal to t minus 1 squared, simply putting this x and t into there, we could get y equals x minus 1 squared. So we've eliminated the parameter, and yes, it is definitely a parabola. Okay, so that is the path, and again, it's kind of just going along here. Perfect. Now we actually already found the value of f, the vector valued function at 2. And again, an emphasis and a stress is that it's a vector. So when we put in 2, for part B, the vector value at 2 is a vector. So it was 2 comma 1. It's the vector 2 comma 1. It's pointing, over 2 up 1. It's pointing in that direction. So that yellow line over here, actually vector, is the solution. That's what that looks like. It's not an ordered pair. Okay, and we drew it. So yay, good for us. Now it says also find the derivative of the vector valued function at 2. And so the derivative of the vector valued function, you just do it component by component. And here's where we start to maybe pick up a bit of our parametric notation in a way, because if if I think about the derivative of that vector, I'm going to differentiate the x component with respect to time, and then the y component with respect to time. So I want to look at that as a vector. So the x component was, now if I look at this function here, it's just t, so its derivative is 1. So then the overall derivative vector, just as a generic vector, is 1 comma, and then I do the derivative of the second component, the y component. It's 2 times t minus 1 to the first power. Technically, there's a chain rule, but its derivative is 1. So we would get the vector 1 comma 2t minus 2. So there's the derivative of f. And we could also think of this as a velocity vector, since the derivative of position is velocity. Now we put in 2, and so we could say f, the vector values function's derivative at 2 is still a vector. It's 1 comma 2 minus 1 is 1. 1 times 2 is 2. 1 comma 2. So there's that vector. Now here's the difference between a velocity vector or a derivative vector versus a position vector. So if you read the part C, it does say, and kind of gives us away, you're going to draw it so that the tail of the velocity vector is at the head of the position vector. And so, this is my, I guess, tip to tail. Maybe that's what I should say, tip to tail, the head or the tail, tip to the tail. So this right here represents the position vector. At that instant, I'm going to write and draw this vector. So from the ending point, that 2 comma 1, what I'm going to do is I'm going to draw a vector that goes over 1 up 2. It looks like this. So this vector right here is the velocity vector, or the derivative vector, and I just drew it right at if I go tip to tail, I drew it right at the tail of that position vector. So tip to tail, so that the tail. So I'm wondering if I have the tip, like maybe I have mixed up the tip and the tail and the head based from honors pre-calc, but that's okay. So and what I want to also emphasize is that since that's really a velocity or a derivative, it should really be the tangent line. So I can see the tangent line at the point of tangency, which is perfect. So again, this has to be drawn at the end of your position vector, and that's its velocity. Okay, so that's kind of just some basics there. And then if I look at the next example, I have another vector valued function. Same idea. It says draw the path from 0 to 2, draw in the derivative of 1 and the position at 1. So, it might be helpful to again think about, okay, at t equals 0, I get the vector 0, comma, 0. At t equals 1, I get 2 comma 5, it looks like. And at t equals 2, I get 4 comma 4 plus 8 is 12, if I did that right, because of 8. Yep, good. So then again, just thinking about if I just were to sketch this, I'd have a vector pointing to 0, 0, which I really can't see, 2, 5. So like maybe I'll just kind of estimate this. 2, 5 is here, and then 4, 12 up here. So I would have, again, each of these represents a vector. So I have a vector staying at 0, and I have a vector pointing at 2, 5, and I have a vector pointing at 4, 12. And so then the path would be something like this. Now, if you wanted the exact image of it, remember this first part is x is equal to 2t. Simply dividing that over to get 1/2 x, that's what your t value would be. And you could easily substitute that in. Remember, the other component, I'll come down here, y equals t squared plus 4t. I could simply substitute 1/2 x for the t. So y equals 1/2 x squared plus 4 times 1/2 x to eliminate the parameter. So that is equal to y is equal to 1/4 x squared plus 2x. So again, parabola, it looks like it's going through 0, 0. And if you wanted to complete the square to find out vertex, you could certainly do that. Okay, we already drew h of 1. So again, just to highlight that, maybe I'll highlight that here in yellow. Here's h of 1 right there. It is a vector, and it's this vector right here pointing to 2, 5. It's a position vector, so it's measured from the origin. If I want to find the derivative at 1, I'm going to start that vector. I'm going to start that vector where that one ended because it should mimic I guess, visually show us that tangent line. Okay, so first of all, let's just get the derivative as a function. Let's find h prime. So h prime of this vector valued function is equal to 2, because that's the derivative of 2t, comma, 2t plus 4. So then I'm going to evaluate the derivative at 1. So the derivative at 1 is equal to the vector 2, comma, 2 times 1 is 2 plus 4 is 6. So I have the vector 2, comma 6. So I would go over 2 up 6 to kind of show like what's happening at that instant. So I kind of over-exaggerated that, but that's okay. Just a sketch. And so this vector right here is drawn from the end of where our position vector landed. So maybe arrow that over just a bit. There it is. Okay. And it is vector 2, comma 6. Okay, excellent. All right, so then I think this is our last example I'm going to look at for this video, because this last one talks about differentiation of a vector value function. And notice that I use, parametric equations, x and y, but that's really easy to represent as a vector because there's an x component in terms of t and a y component in terms of t. So I could just rewrite this if I really wanted to and say, hey, what if it was just, some position s as a vector valued function whose x position was 1/2 t squared and whose y position was sine of 2t. So vectors and parametrics work interchangeably, and I hope you see that. Okay, so it says find the slope of the path of the particle at time t equals pi 6. So if, thinking back to finding, how do I find dy dx when I have parametrics? You simply find dy dt and you compare it to dx dt. And so again, here's our y. So the derivative of that would be 2 cosine of 2t. See that chain rule? And then dx dt would be 1/2 times 2 is just 1, so just a t. So now we evaluate that when t is equal to pi over 6. Well, okay, so pi over 6, but I'm doubling that, so it's pi thirds. So that's really a 60-degree angle that's going to be evaluated. So there's 1, 2, root 3. So the cosine of that is 1/2. So then we get 2 times 1/2, which is 1, divided by pi 6, which is 1 over pi 6, which gives us the nice number of 6 over pi. So that's the slope right? That's the slope. It's a scalar value, right? There's no vector to it. That's the slope of the path of the particle. That's really the derivative of the tangent line if I were to graph out the path of the particle. Now, it asks us to write a velocity vector. So we already have the two components in a position vector. So our velocity vector would just be the derivative of each of those components. And we kind of already did our work over here. We're just going to put it in vector format. So our velocity vector, which is the derivative, could be equal to t comma 2 cosine of 2t. So again, this concept of vectors and parametrics really work hand in hand. Okay, now speed of the particle at this time. Well, speed is a scalar measurement. It's the absolute value of velocity. And so if I want to find the speed, I'm looking at this vector velocity as like the magnitude of that. So what I want to do is figure out part C here. So sometimes you'll see like a double, almost looks like double absolute value. That's referring to the magnitude of that vector. And so we want to find almost thinking about it as the Pythagorean theorem. You know, if I'm going over a certain amount and up a certain amount, I just want to do that component squared plus the other component squared. So it's kind of like the derivative at x squared, and then add to the component that represented the derivative of y squared. And so I already have these components squared. So then I would say, okay, I could figure out that's the square root of whatever t squared is plus 2 cosine of 2t squared. But we're evaluating it at pi 6. So when we put pi 6 in, remember, we got a value of 1 and a value of pi over 6 for our components. So then once I do that, so now we have the 1 squared plus pi over 6 squared. So that could be equal to 1 plus pi squared over 36. Now, if you want to combine that to make it the square root of 36 plus pi squared over the square root of 36, which is 6, that is fine too. But that is the speed. Now, this is a scalar. In other words, it's not a vector. It doesn't have two components, but the vector that I started with, 1 comma pi 6, does represent the vector that is its velocity at that instant. Okay, now the last thing is we want to set up an integral to represent the distance. And so again, we're basically going to integrate this particular function just from 0 to 5. So we could look at our vector almost like thinking about it in terms of arc length. And that's exactly sort of where this formula should look familiar from parametric arc length. And we will just go ahead and set up an integral. Let's choose that purpley color. So from 0 to 5, so it would be from 0 to 5 of the square root of our dx dt squared, so t squared plus 2 cosine of 2, t is a quantity, squared dt. And that's it. There is an integral that represents the distance traveled, the total distance traveled from 0 to 5. And again, that should look familiar to parametric arc length. And again, if you think about why does that work, and if you go back to our other examples, like even thinking here, I know it's a different example, but you're basically measuring your arc length of that curve, which is exactly this formula right here. There's your arc length, and we would just integrate it from A to B. Okay, so the next 3 examples, 4, 5, and 6, will be in the next video. So you have enough, hopefully enough in terms of, just familiarity of how it might be asked on AP exam, and then, you'll be able to do that first homework worksheet.